today we are going to speak about chapter 5, that is about interactions. Anyway, first I will do a very quick recap of everything we have seen so far in the What If book. So in chapter 1, we mainly started with the fundamental of causal inference. We introduced the notation, counterfactual outcomes, and yeah. So then in chapter 2, gave us the setup to run causal inference. It was like through randomized experiments, or also like conditional randomization. It also provided us the method to compute the causal effects. Then chapter 3 told us that life is not perfect, so we cannot run randomized experiments all the time. So we needed to use observational data, and they provide us the theoretical conditions in which observational study can become a target trial and thereby a randomized experiment. And then in the last week, Simon presented the effect modification, so studying the effects in strata of the population. Also, it provides some adjustment methods. And after that, as I said, we're going to study interactions. So the problem is, so we start with the problem that almost all chapters start with. So imagine that we want to see if you look up, the person like in front of you will also look up, but now we are going to make it even more fun. So we do not only care about if the person will look up when you look up, but also if it will look up when you are naked, or yeah, I think it is not necessary like to run an experiment for this. I mean, I think people will just turn around, like, or if it will have any effect if you are dressed. So what you are doing is studying if the two interactions have an effect on each other. We are gonna give like a formal definition of this through two different frameworks. One is the one that we're always using, that is the counterfactual framework, and the other one is the so it's the sufficient component cost framework, that we also saw that it have its advantages, like overall from the teaching point of view, but it also have many disadvantages from the analytic point of view. We'll go on that afterwards. So going back to another example that we have already treated. So we have this experiment where we have a treatment that is to do the hair transplant when A is equal to 1, and to not do the hair transplant when A is equal to 0. But we are going to also have another treatment, that is if the individual took a multi-complex of magic vitamins. So just or if this individual didn't take these vitamins, and then the outcome will be again. So 1 if the individual dies, 0 if it survives. So we are going to study the causal effect of these variables in the outcome. As we have two treatments, not only one as before, we also have more counterfactual outcomes. So right now, we are gonna be dealing with while so these 4 outcomes as we are considering dichotomous variables and dichotomous treatment and dichotomous outcomes. So we are gonna be making intervention in both treatment, and so when we do intervention in more than one treatment, we call it joint intervention. Okay. So once that we have introduced all that notation, what we want to see is that there is like we want to identify an interaction, and that will be if the causal effect of treatment A on Y will be different depending on the values of E. That thing a little bit more formally will be like using the causal risk difference. So an additive scale will be the same to say that the outcome when 2 treatments at 1 is equal to 1, so the difference. I will just write this very fast. I mean, this is kind of similar, it's quite similar to what we have been doing so far. So it's basically grading the risk difference, the causal risk difference, to measure the causal effect. So we will say okay, so this is basically saying when these 2 quantities are not equal, it means that the value of E has an effect on the quantity, on the causal effects. So there is an interaction. If you do some algebra, you could change this for this, and you will have the same definition, but depending instead of on E on A. So what this definition gives is an equal status to treatment A to E. So both are the same of important. And in fact, this is a significant difference with effect modification. That is what Simone explained last week, because with effect modification, you are computing the causal effects on modifier variables, but modifier variables cannot be considered as treatment. So you are not gonna be defining like a counterfactual outcome like this. I mean, this is wrong, because you cannot modify that. You cannot modify that one. You cannot treat it as a variable, and that's one significant point that it makes. And why is this? Because
sorry. So can you explain this one that you have YA?
Yeah, like so for the notation, like you are not. So it says that you cannot define a counterfactual like this, in the sense that you are not. Sorry, so I think I explained it too fast. So you are not gonna be interchanging. Like basically, as I understood with the notation, is that I mean, it has a different conceptual meaning, so you shouldn't be changing that.
But B, what was it?
B is an effect modifier variable. So yeah, that's like the notation from the previous section. Thank you for the.
Mathematics might be the same, right? So mathematics might be the same. It's just that you
Yeah,
mathematics because you cannot swap these things by definition. But in the case of Simons, you could put something like that.
Yeah, so that's the thing. In fact, we will see that in certain conditions, this situation will be the same as when there is like a modifier. So I mean, I can say it now. So when variable A is randomized, you at the end of the day you will it's kind of equivalent to an effect modification, and you can compute it in the same way. So yes. Okay, so I will go here. Yeah, where's the So in the past sections, we said that for computing the causal effects, we need randomization because they provide exchangeability, also positivity and consistency. And we needed that for the treatment. So right now, as we are dealing with two treatments, we need it for both of them to do the same. And in fact, to compute, like according to because all this is with the counterfactual framework, so to compute the causal effect, we're gonna be considering different cases. The first case is that E is random. So when E is random, because of the exchangeability, you can say you can say that this joint counterfactual is equal to this quantity. So we can use this expression to substitute over here, and with that I mean, should I regret it again? I mean, it's like once you have this equality, you can do it for each one of them. And then with the method that we explained in the last section, you will be able to compute the causal effect. In fact, this is like, as you noted before, it's like the same as the effect modification. So, because when you have E randomized, they're equivalent. So then imagine that we are not, we don't have it randomized. So what we could do is like trying to condition on it, as it was kind of explained in section 3, and try to see the way that it has the identifying conditions, and we can run like the IP weighting method and the standardization method to compute the causal effect. And there is like another way to compute the causal effect that I think it was quite smart. So instead of considering like the two variables like this, they were saying, why don't we just like mix them and consider like a unique variable? it will be AE, and their values will be so 0, 1. So in this way, you can compute it like as a one treatment causal effect. So basically, it shows like the ways to compute the causal effect, this section of the chapter. So how to compute the causal effect on this with the joint intervention, and it gave like these three conditions. So when E is randomized, when it's not randomized, like so it's kind of similar as how it was explained in the observational study. You have to look for the condition that we split. And then the last one that I think it was quite smart to consider just as a variable. Then for all of this, we might just use IP weighting or standardization.
Sorry, Chema.
Yeah.
In this case, you are projecting the two variables in a single one,
Yeah.
single dimension.
Yeah, that's it. You consider that the treatment, instead of having being dichotomous, is gonna be like with 4 classes. So it will, so you will have to like to do the same process, but consider it like more classes. Yeah. So, okay. So like until this section in the book, like and we've been considering the deterministic outcome because it made our life easier, but it might be also applied to stochastic ones. But for this specific section, we have to consider that they are deterministic, and also we have to assume that they are dichotomous. Because I am going to introduce like the this other framework that is the sufficient component cause framework. So the first thing that we can do is like classify the individuals depending on the.
So basically, everything in this case is just redefine this with 4 classes and then repeat what we have been doing.
Yeah, that's it. Always you have to have the 3 magic conditions, like but that will be. So then like.
And we need to make the distinction on randomized or observational, but the story can be repeated.
Yeah. So then once that we have all the outcome of the individuals, what we can do is classify these individuals depending on the response of their counterfactual outcomes. In fact, if we consider table 1.1 or table 4.1, like all the individuals can be classified in one of these classes. So this will be, so it can be that when the treatment is equal to 0 is 1, and when the treatment is equal to 1, also the outcome is 1. The same here, so it doesn't, regardless of the treatment, both are 0. So we have for that case 4 classes, and these are, and each one of these is a response type. That is the combination of the counterfactual responses. And then it becomes even funnier when you have 2 variables, because instead of having 4 response types, you're going to have 16 of them. So for each, so you have the 2 variables. This will be the intervention that you make, and this will be like the response. So you will have 16 different types. Or, I mean, to be more accurate, you may have 16 possible types. If in the data there isn't one of those individuals, you are not going to have that type. And what I will be doing now is explore the relation between the responses type, and with this we can study also the interaction between the treatments. So for example, how can we like understand type 1? We can say that regardless of the treatment that you do to this individual, this people is gonna die. So this will be type 1. We're gonna mark it. Then what happened with type 16? It happened the opposite. It doesn't matter what you do, that person is immune. Will survive, probably this fails. So I would like to ask you, what will happen if all the individuals in the population will be from these two types?
Can you repeat?
Yeah, so if all the individuals in your population, in your data, will belong to one of these two types, what will that mean?
With just one of them?
Or 1 or 16.
Then there won't be any causal effect of any treatment?
Yeah, that's it. So in that case, the SAR causal null hypothesis will be also true, meaning that there's no causal effect in any individual. So it's kind of one of these extreme cases. So then there are also other types that are quite interesting. So for example, so we have a type 4. Type 4 means what happened to type 4 is, so these people, this person will die if he takes vitamins. And type 6, for example, will only die if treated with a hair transplant. And then we have kind of the opposite. Type 11 will only die if not treated with the hair transplant. And type 13 will only die if treated with vitamins. This is kind of clear. Okay. So what happens? So if now all the individuals in the population will belong to this any of these types, what we can guess is that there won't be interaction between the variables, because one is independent to the other. Can we see that? So that will mean that, for example, in this quantity over here, there will be unequal. And in order to there be an interaction, we can define 3 other classes. For example, the class composed by 8, 12, 14, and 15. 13 that that are those that develop the outcome are those that only are treated in one of the variables, because then there will be interaction between the two treatments. As this, there is another class that will be the individuals are treated in 3 of the treatments, and then if they are treated in the opposites. So, for example, the vitamin is 1, but the hair transplant is 0, and vice versa. So, with this, what all this means is that to there be an interaction, the individuals have to belong to any of these 3 classes. If not, there won't be interaction. So we are understanding the mechanism, like from where the effect in one variable to the other comes from. And yeah, so this was like just a little example to explain. And then, so let's go back to the original example with just one variable. I just show here. So when A is equal to 1, so yeah, we cannot say that A equal to 1 is the only cause for death, because there is also one. Yes. Because there are cases when it is also 0, so that means that it depends on more variables. We are gonna call these background effects. So so I can say that so to illustrate this case, the book says, so suppose that the person will die if have a hair transplant, but also this case was yeah, I don't remember the sad example. So yeah, so it was allergic to anesthesia. So what it is saying is that by itself it cannot explain the death, but if we suppose that there are background effects, we can assume that these are gonna be the cause. In particular, we are gonna call these effects U1. So maybe I use a different one. And then we can say that this is a sufficient cause, a minimal sufficient cause to for the death. The same we can do like in the opposite. Suppose like with so with A equal to 0, we cannot explain death neither, because there are outcomes that are 1, another are 0. So we have to suppose, yeah.
What is U sub 1 and A sub 1?
Sorry, A sub 1, no, it's sorry, A equal to 1, sorry. So yeah, we are saying that the hair transplant plus the background effect, that is in this case will be the allergic to the anesthesia, will provoke death. So this is like the sufficient cause. On the other side, when there is
why not just the anesthesia allergy? I mean, he or she's dying because of the anesthesia allergy?
No, we are supposing that it is because of both. Because then there will be another, because then what it says that there is another case that, so I mean what it does is to define 3 cases. in particular, so yeah, I write them. So what it's saying is that because of background effects that we might not know, there are like 3 minimal causes to provoke death. So one is, for example, this background effect, U1, that might be the anesthesia. Then when there is no hair transplant, it might be another different hair effect, background effects that are low ejection. And last, let's say to make consistent all the response types, there will be another background effects that are, for example, pancreatic cancer. So we can define, so we can represent all these sufficient cause, which are composed by components. Each of these one will be a component as a causal pipe, like a diagram that will.
The third one, there's no A.
Sorry?
The third one is U sub 0 equals 1. Is there A?
No, because it's just background, some background effects by themselves.
But there's a Y equal 1.
Yeah,
Yeah.
sorry. So this will be the sufficient cause for death. We can represent these ones. I mean, it's just a diagram to represent those components. So yeah, this is trying to explain graphically where the causal effect comes from. So what I am just doing is like in a graphical representation to summarize the minimal cost.
Sorry.
Yeah.
In the last one, shouldn't it be U sub 0 equals 1?
Sorry. Yeah. Oh. And then the chapter also says that this is also for pedagogic aims. This is quite helpful because it might give you the intuition of the importance of the effect modifiers on the outcomes, because so this can give you the idea that the proportion of this variable that might be a effect modifier that we are calling now backtracking effects will also produce bigger or lower causal effects. What I mean with this, so the sign will be the same, but the magnitude will be different, because consider, for example, a case where you have individuals that have this backtracking effect. So consider two populations, one where the population, so 10% of the population will have that variable, and so this is the first case, and the second case where it will be just 1%. So the causal effect will be, will have the same sign, but as there are many more individuals that may have a sufficient cause for death, more people will have that outcome. So the magnitude, so the number of the causal effect will be bigger. Is that clear? Yeah, so
can you explain again the 1 and 2?
yes.
The one is if I.
So yeah, if we consider two two parallel worlds with two populations. So in one of those populations, 10% of the people will have this effect modifier. In the other one, just 1%.
So in this example was that if I'm allergic to anesthesia,
Yeah, so imagine like in one population, 10% of the people will be allergic to anesthesia, in the other one, just 1%. So because of this, as it is part of the of a sufficient cause, as more people will have this sufficient cause, the causal effect will be also bigger, because what you are making is this is provoking that more people have the counterfactual outcome 1. Yeah. Yeah, and then basically so this can also be done for the other case, where you have like many more types. But so it is what I said before. So these are the possible types, but it might be that in your population, in the data you're analyzing, you don't have one of those sufficient cause. So you may only have 8 of those situations, for example. So what I want to make clear that these are the possible ones, but then depending on your data, you will have more or less minimal cost.
so you're saying that you have observed only from 8, not the 16, but the 8, or is that what you're trying to do?
Yeah, I am saying that. So okay. So these are the system. Okay, these are the types. Okay, but from the type you can obtain the minimum cost. So let's say I see them as like these conditions, like that will provoke death. So analyzing all these cases, I can say that when people have a hair transplant and do not take vitamins, assuming some backtracking effects, their outcome will be death. So yeah, so a little summary. So basically, also for the small, also for the small case, you have the types, and from the types you can create this minimal cost that can be represented graphically. And this minimal cost will be the conditions that will provoke that your outcome is 1.
And these are created based on the expertise of in this case, the doctors?
I think it's created. Sorry, data. Based on the data, right?
Yeah, based on the data, on the condition that you got. So it's like you analyze so you analyze the data, then from the data you can get the types, from the type you get the conditions, or they call them sufficient causes, and that's the name of the sufficient component cost framework. And from this you have these diagrams that are also called causal bias diagrams.
It's contingent then to the data that you have. So you might have the same scenario underlying, but if you have a different data, then you might have different set of minimal causes.
Yeah. So yeah, that's one also.
So it's not that you have experts or anything.
Yeah,
So
and you know,
the data, right?
I don't understand that. It seems that the 9 different pies are actually independent of the data. I mean, they are just created by decree. They are the only 9 possible exhaustive ways in which you could have that, right? I don't think it's based on any
Yeah,
But that's
observed
the theory.
data.
That's the theory. So this, I think, on these 9 cases, this is the theoretical possibility. But then what you obtain at the end is out of your data, you define the use.
Oh,
And it might be that you don't
How
have
do
the
you
data
find the actual?
to achieve all these 9 different types.
So you're saying that like giving meaning, providing content to the actual use is something you do based on your observed data.
Yeah.
But at the same time, like the 9 things over those, like they are independent of your.
Yeah, so let's say you have a first like a overview, and then on your data, you can select the causes. So it's like you have a big selection of causes, and then depending on your data, you might have to remove some of them.
You might have to remove some of those 9.
Yeah, that's it. So imagine, for example, that you don't have some of these cases in your data, so then some of these diagram won't hold anymore.
So you can have at most 9, but you could in a particular case have a lot fewer.
As I understood, like the theory is like that, yeah. Okay. Then, so yeah, from all this, you can also.
And in this, you have U0, U1, U2, blah, 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 U8. These U8 are different. So in one case was anesthesia.
Yeah.
Therapy.
So those are like, they're called background effects. So it's like, I mean, it's like to make, so like to make all the, how can you say? So this will be kind of a disaster bag where you put all the effects that you don't know. So it holds that this backtracking effect plus the other 2 treatments for sure are gonna cause death. I mean, here we just call a variable, but it might be so many variables.
But then they are recording all these 9 things, or?
I mean, at least, so yeah, that's another thing they comment, that this might give you an intuition. So with this framework, you might have an intuition of the causal effects behind, but yeah, like you may have to maybe take them or maybe with expert knowledge. Yeah, and then so from here, yeah, so I might just do this. So yeah, so then we have like also like the difference to compute the counterfactual interaction. So in the counterfactual framework, you get the quantities, you compute the ratio, the difference, and depending on that, you can assume that you have an effect. But with this framework, what you will do is, like, for example, if I want to know that A and E have an interaction when they are both ones, I will look if I have like one of those conditions that in this case I have. I will check then that, and then from there I will check the, for example, I will check the outcome, and then I will see that there are like other sufficient conditions there that there should be. If they are in your data, you have not removed it before. That have this. So at the end, it's like more. So from the drawings, it's like you have to induce that changing one of the treatments, the outcome will change. This is like so this is a little bit more, let's say, I mean, you may know where it comes from, but it's not as straightforward as the other method. So, I mean, one of the main things they're saying is, so, you know, like with all this framework, you may know where all the costs and everything come from. You may know the knowledge behind, but it has its cost. While with the other, it's more about assuming the conditions, computing the quantities, and from the value of the causal effect, the causal rate, the causal difference, you will have if there is a causal effect. Then, so yeah, so what else? So it says that, for example, so it made a difference when there is an interaction that have two is like A equal to 1, E equal to 1. This is called synergetic interaction. You see that there is like interaction between those, but if you see that the variables are that if you define the interaction in this framework as this will be an antagonist. I mean, I think this is more a matter of definitions. Yeah, so then the chapter finishes with a general discussion where it says that both frameworks, so first of all, it says that they address different questions. Like, so the counterfactual framework, that is the one that we are used to, address the question what happens and what will have happened if you would have changed a certain factor, while the other is how does it happen, and that's big why we got the causes and everything. So then it basically says that from the data analysis point of view, this framework might not be useful because of the assumption that you have to take that the deterministic, dichotomous, I mean, there are extensions, but they're not still yet sophisticated enough for data analysis purposes. But still for education, like to show some of the causal concepts are fine. Yeah, it says that in that case, the counterfactual framework might be more useful to study causality.
So what's the name of the second framework again?
Is sufficient components cost framework. Because so each one of those, so the name comes from, so okay, I remove it, but you know, so when I write before like this one, so this is a sufficient cost, and each one of these is a component, so that's why.
So the next one gives a third framework, which is based on causal graphs.
I have not checked it. Okay.
I never get something. And then there's an integration between counterfactuals and graphs.
I mean, any questions or any questions come? Yeah, so like for me, like the main grasp of the chapter is okay. We saw you two frameworks. This one, like I mean, you put many more conditions. You might kind of understand better where the interaction comes from and why the causal effect comes from, because you are analyzing with the sufficient causes. But at the end of the day, for like, let's say, working purposes, it's not sophisticated enough. I mean, for a casual inference class like this one, perfect. But, I mean, that's at least what I got from the chat.